Okay, we should start. So today we start a whole new set of models, which is going to be exciting. I hope you're tired of the matching pennies models. But let me see. First, how did it go with Melina? I heard from her, but I also want to have your opinion. Good. How was the level? Because I know that we have covered a bit of the Rescola Wagner, but she wanted to add an extra effort-based component. Was it just?
I think it was good conceptually. I think it was difficult in the second class. We had to like implement the thing. Like it was nice that we at the end like went through the whole full code because there's no chance we would be able to do all of it.
Yeah, not yet.
Yeah, not yet.
And only 2 hours.
Or like in that time frame. Yeah. I think it was the conception quite good, but she was really, really good at this game. I felt like it was very 2 hours or so.
Nice. Yeah. And also see how people have went on using this stuff. Yes.
I think the individual concepts were actually understandable, but at least many of them, but it's hard to see how they play together. And also maybe kind of have to dig into the code afterwards. There's just a lot of steps that keep in your head.
Okay, so
had to get a long way during the 2 hours, but still you got an appreciation of it.
Yeah, the overall how these things fit together. Yeah. Yes.
I think it was really nice to also get an idea of what sort of complexity a model that is actually used in a scientific or like academic setting.
Yes.
Just having the reinforcement learning around with or something that level. It was nice to see, okay, I think at least in our group we talked about like why do prior predictive checks when we have one prior?
Yeah.
And now it makes sense that okay, when you have a complex model like this,
you want to do that. Yeah. Also, like I always start thinking, okay, this year I'm gonna have this model and this model and this model, and then I run through all that I need to sort of teach about the foundation, and I just okay, I'm gonna stick to the simpler one. But we'll see how far we go with the Bayesian models. I'm also have ambitious plan for the last moving beyond Markov chain Monte Carlos into amortized inference, which is the whole new sexy thing. But we'll see. Okay. So this is good and useful. I'll also talk to Melina again. Now, I asked you to look at a conceptual intro to the models that we're going to discuss because I have a lot of materials I want to go through. I'm not going to ask who watched it or not, but I'm going to ask if you have questions on that specific aspect. Right, so the whole idea that the Bayes theorem that we've seen so far as a tool to fit models can also be used as an actual model of cognition. And we can see that in perception, where, for instance, a lot of perceptual illusion are due to our pre-existing priors on how the world looks like, but also on multimodal integration, where, you know, the McGurk effect, the kind of thing. The way that we perceive a sound is shaped also by the visual stimuli that we're receiving, but also that what we call social cognition can be seen as an instance of Bayesian integration of information that we have, that we're perceiving, but also that others are giving us, right? Does that make sense as a general idea? Did you have questions on those contents? Yes.
I have one, but it might be a very big question.
Well,
So I understand
Bayesian updating as you're just updating according to the rules of probability theory.
Yeah.
And I guess what I'm asking is how would that ever not be the case for the brain? But supposing that's like a product of evolution. I'm supposing evolution would probably have designed our brains to be as good as they can get at estimating probabilities or whatever, like I guess making inference.
Okay, this is an excellent question, and it has two aspects. So one is, it's a bit about actually the implementation. Why not the full Bayesian updating that we've been doing? And the second is about what are the limits of these frameworks, right? So let's start with the first one. Why not Bayesian updating? So the first one is that MC, which is our best shot. Well, we'll see another one with amortized inference, but so far it's the best shot that we have at implementing Bayesian updating. It's very computationally heavy. Right? We do really simple models. What the brain is doing is much more complex, integrating a lot more things. Would it be able to run that kind of sampling in real time? And to that, there's a few different answers. For instance, Pathfinder, which we've seen in earlier classes, is an attempt at producing a very fast Bayesian inference at the cost of precision. Variational inference, that's something that Pedagul is very keen on, is also another way of approximating fast Bayesian inferences. To the point that some people are saying, I wouldn't trust those tools as ways of fitting my models, but they are very interesting tools to explore cognition. So Bayesian updating is very expensive, and the implementation might pose some challenges. The second one is that, as we will discuss perhaps a bit more when we go into the categorization module, the final module of the course, Bayesian updates assumes that you already have the units that you are updating. Let me rephrase. So let's say that you need to figure out which grammatical rule, grammatical structure for a sentence is the one you should use. When do you have to do the stupid inversions that you days love so much, right? So what you have, if you want to do a Bayesian model of that, is a few candidate structures, few candidate word orders, right? And as you go through the word, right, as you meet sentences, you update the probability of each of them. But that assumes that you already have those structures. Where do the structures come from? And that's not something that Bayesian update is very good at doing. So a lot of people, like Tom Griffith, for instance, would say, oh, well, actually, that's what connectionism is for. Right. You have neural networks that can sort of create these temporary representation by co-occurrence of stimuli, blah, blah, blah. And then once you have those, you can use Bayesian update to sort of decide which of these potential representations are different, which is not how a lot of these neural networks work. But it is a big issue that Bayesian updates is not a very good model for how these representations emerge. When we'll do categorization, again, we will see that certain models of how we categorize objects in the words as dogs or cats or, promising students to drag to our study group are actually pretty much intractable in traditional Bayesian update. And we need to use different tools to sort of figure out how these rules emerge or even how these rules are adjudicated. Does that make sense? So as all models, well, it is a particularly powerful model, but as all models, it has limitations. Good. More questions? Well, then what we're going to do is, well, before what we did with the matching panels for pedagogical reasons is we have a task, we have a behavior that we observed, and now we wanted to figure out cognitive models that could explain that behavior, which is not the only way of going at cognitive modeling. For instance, another very good approach is to start from theory. We have some basic cognitive principles, and then we can use these principles to create models that will predict and describe behavior across a wide variety of tasks. So we could have done it with reinforcement learning, but I actually wanted to do the whole, here is a task, let's think through things. This time, what we're going to do is the opposite movement, which is we'll start from the idea of cognition as a Bayesian system that integrates information. And then we will see how this can be declined across a wide variety of tasks. In particular, we'll see a few very briefly, one more in detail today, and in the next assignment, you have to sort of think through how you adjust this model to a different task. And since I worked for a while in how we integrate direct and social information, that's where the examples are gonna come. So this is we're just scratching the surface. There's increasingly many good books on these topics. Two technical ones are the Bayesian models of perception and action that really goes into the nitty-gritty details of how Bayes has been used to model very concrete perceptual and active motor processes. The other one is a broader perspective, Bayesian models of cognition, which also discusses a lot the philosophy of Bayesian models of cognition. It's pretty thick, it's pretty big. I haven't finished reading it yet, but it's pretty good. If you want something that's a bit more pop, there's the Laws of Cognition, which Tom Griffith has published a few months ago, which is going through a lot of those concepts, but just in a very discursive way. Just a reminder of Bayes' rules, right? This is Bayes' theorem. We have that our posterior, the probability of A given B, is defined by our prior. So how likely is the explanation X before we even see the data? How then multiplied by the likelihood, how likely is the data given the explanation? And then that's the posterior, which gets out. How likely is the explanation given the data and the prior? And then we have something that we often try to forget, which is the probability of the data independently of the explanation, which is useful because if you have two probabilities multiplied by each other, you tend to get to very small numbers, and the denominators is used to sort of bring up, given how many possible explanations you have, their probability should sum up to 1. Brings it back to the right scale. And we've also seen, right, that if you have prior is here and the likelihood is here, the posterior is combining their information in two important ways. One is where is our mean expectation, which is not exactly, but somewhere in the middle. Why not exactly? Because the second aspect that it tries to integrate is how confident prior and the likelihood are. The more confident they are, the more influential they are. So we see that actually the mean expected is slightly closer to the likelihood, which was more confident than it is to the prior. And the confidence of the posterior is much higher than both the prior and the likelihood, because it's learning from both. we'll go through these things more in detail as we implement, but this was just to give you the grand thing, so you're all fresh. And often we talk about Bayes' theorem as the rational integration of two information sources. What do we mean by rational? We mean that we try to make an optimal use of the information. If this is your prime and this is your likelihood, the rational decision is to change your belief in these ways. Because you're using their confidence, right? It's a precision weighted average between the different sources of information. It's not just looking at the means, it's also looking at how confident they are. And it's taking these information at face value, right? It's saying, these is the prime, and we believe in it. This is the likelihood, and we believe in it. If we take those information at face value, what should we believe? Okay, and now I'm slipping to, I know myself, so I needed to put a placeholder to tell me not to go into a rant about everything else. Good. So let's start with a concrete example and see how we can implement Bayes' theorem as a way of integrating information. So imagine you have an urn which has blue marbles and red marbles. It's tendentially called a polia urn, and statisticians and people working in the Bayesian field really love these urns because they're easier to model. So that's why we're starting with that. And the task that you have is, if you don't know what's inside the urn, you need to guess which color the next marble that you're going to sample will be. So that's your task. You have to say blue or red. You have some information, two sources of evidence. First, you have a prior. So you went on the internet and you read that 2/3 of urns just like these contain more blue marbles than red marbles. In particular, 2/3 of the marbles are blue, which is roughly 0.66. Bayes is completely information agnostic, so it could also be, oh, you meet your friend and your friend says, well, I took 3 marbles out and 2 were blue. Same kind of information. Then you have a likelihood, so you can pick 3 marbles from the urn, and 2 are blue. So this also tells you that 2 out of 3, or roughly 0.66, are out of a 0 to 1 scale, are blue, right? So 60, I should have written 67, but 66% probability that the next marble is going to be blue. Are you on? Yes. So when we combine the two sources of evidence, right, we have now more evidence than just having one, that the blue marbles are more likely than the red ones. Right? But we need to calculate by how much. So we take Bayes as optimal, right? We say that each source of information tells us something about a possible binary choice, probability between 0 and 1. And each source of information is optimally combined. That is, it's taken at face value. We're not questioning whether our friends or the internet are reliable, right? So what we can do is we say, given that it says that our friend says that they sampled 3 of these marbles and 2 of them were blue, we can use the binom to draw the underlying probability distribution of the rate of marbles being blue. Does that make sense? So given that we've seen 2 out of 3, What's the probability that the true underlying rate is 10%? What's the probability that it's 20%? And so on and so forth. Then we take the likelihood and we do exactly the same. And since in these examples they're the same, right? We end up with the same probability distribution. And then what we do is we want to end up with the probability distribution of our posterior. Right. We can get there in a few different ways. So, first of all, can you see any difference between the two, well, between the prior and likelihood on the one hand and the posterior on the other hand? Yes?
Pretty sure that's centered around the same value, maximum value is the same, but that this variance.
Yes, exactly. So the means are the same, right? So it stays the same, but the variance is shrunk. So if we're actually trying to guess whether the next marble is going to be blue, we're actually more confident that it's going to be blue, right? If we're trying to guess the underlying ratio of blue to red marbles, its average expected value is unchanged, but our confidence in that the next blue marble is going to be blue, the next marble is going to be blue, it's higher. Does that make sense? That's something that really confused me at start. So that's why I'm spending a bit of time on this. So, yes. So how do we go and implement that? And I know that Martin has done something like that in assignment number 2. So
Yeah.
Yeah, that's not. So how do we go and implement that sort of process that we've seen?
Which process in particular?
Well, going from our two-thirds to the full posterior after. Yes, we had something.
I mean, we've been using Markov chain once counted
Mm-hmm.
to do that exact thing.
Yeah, but I want a bit more concrete. How do we implement that?
If it was then, I would write a program instead,
Mm-hmm.
specifying that the likelihood is binomial,
Mm-hmm.
and that we have a prior.
Yeah. So you're gonna get into a bit of an issue.
Yeah.
Because if you infer the underlying rate distribution in one case, and the underlying rate distribution, so for the prior and the underlying rate distribution for the posterior, for the likelihood, sorry, and then you try to put them together, you are working in a finite sampling environment, and the thing is not completely, it's non-trivial how to implement.
Yeah, I guess we also don't have data.
Yes, well, we have the two-thirds, right? Yeah.
I mean, from watching your video, you talk about converting the probabilities to log odds, so it's not like a restricted scale.
Okay. Yeah, good. I'll follow up on that. I'll just also hear Martin.
Yeah, so the problem with using MCMC for this is if you want to build a model that internally uses MCMC, it's not going to be differentiable. So you won't be able to use the NOTS algorithm. So I think what you're trying to get at is like a conjugate update.
For instance.
Yeah.
Let's see. Yeah.
And
We'll get there.
Yeah.
I'll stop you there. So let's start with your point, right? If you read the paper that was in the readings for today or watched the video, there is a trick that is commonly used in the literature, which is using, instead of probability, log odds. And we'll see its limitations in a bit, and then why we move on to conjugate reasoning, as Martin was pointing to. So both sources say more red than blue. The agent is even more likely to say blue, right? So what we do is we take our Bayes theorem, we turn it into a log odd space, and given that there is involved a logarithmic transformation, we transform the multiplication into a So multiplication in linear space in a logarithmic space becomes
Summation.
a summation. So we have that the log odds of P of the probability of the likelihood plus the probability plus the log odds of the prior are equal to the log odds of the posterior, or are proportional to the log odds of the posterior. So what we can say is that the log odds of 0.66 plus the log odds of 0.66 give us 0.69 plus 0.69, which is 1.386, which is the log odds of the posterior, which, if we do the inverse logic, gives us 0.8, right? Our belief that the next marble is going to be blue has increased, right? Because we saw that when I sample and when you sample, we get more blue than red. Does that make sense? Yes.
But is this the point estimate of the ratio of red to blue? We don't want that to change, right? We still want that to be.
Well, that's exactly. So what are we modeling, right? So are we trying to model whether we should change the money we bet in the next one being blue, right? Or are we modeling our internal belief of the ratio between red and blue, and then using that to determine our decision? And as we simplify, for instance, in this way, right, we need to make a choice. This is one possible choice. The other possible choice is that both sources, as you were saying, say it's 2/3 blue. The fact that we get two sources saying that reinforces our belief that the underlying rate is 0.66. So if we want to get there with a log odds trick, what we do is we transform that into a weighted average, right? Where each source counts for half. 0.5 times the logit blah, blah, blah. And then we get that 0.5 times 0.69 plus 0.5 times 0.69 gives exactly 0.69. The average between the two is the same. We retransform it, right? And now we have two separate conceptualizations which are answering two slightly different questions. And if you go and read the literature, some use the one, some use the other. And that's messy. So I published a paper doing that, so it's very understandable. But now that we've gone through all these modeling and procedures, can we actually figure out a better way of doing this that maintains both aspects? At the same time that our estimate of the underlying ratio is 0.66, and that our confidence in that the next marble is going to be blue has increased. Does that make sense? So while the first couple of years that took this class had to model the log odds, you're so lucky because we're going to work with the beta distribution. And this is really based on the intuition that if I sample 2 out of 3 blue marbles, you sample 2 out of 3 blue marbles, what stops us from just saying 4 out of 6? Right? From just accumulating the evidence as if the sampling had been 1. Does that make sense? So a posterior probability, any probability, so also a posterior probability, can be modeled as a beta distribution. And the beta distribution has 2 intuitive parameters. It's hard to read, so I'm reading it aloud. The alpha, which is the number of ones that you've observed, the blue marbles, and the beta, which is the number of zeros that is the red marble. This means that we can easily update the distribution by just adding the observations to our parameters instead of having to reconstruct the underlying rate. Because we can reconstruct it after adding, right? We add to the parameters, and those two parameters give us the resulting distribution. We get a new observation. Instead of trying to combine that distribution with the underlying distribution of the new observation, we just add the new observation to the parameter directly. And that's what Martin was saying. We need to move into the conjugate domain, which simply means, well, it means a lot of different things, but in this case, it means that the scale of the parameters is the same scale as our observations, so we can add them directly. So if we assume a prior of alpha 1 and beta 1, right, it's a flat distribution. We can update it by saying that the posterior is equal to the beta, where alpha is equal to alpha plus the blue marbles, and beta is equal to beta plus the red marbles. And then what the beta, so usually I see these things, it makes a lot of sense, and then I'm just, how do I go from this to the actual distribution, right? And I put the mathematical formula here, that the rate, the probability of any given value of theta, given the data, given the blue and red multiple observations, is given by your value of theta to the power of alpha plus the blue marbles minus 1 times 1 minus theta, blah, 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 right? And then you can repeat that for all the possible values of theta, and you get the distribution. Luckily, the computer does that for you, right? So we don't need to keep in mind the full distribution. We can just pass the updated parameters as counts and add the new info as it counts. And we get, when we need it, the full distribution. Yes.
Is data, is that
The rate.
rate?
Yeah, sorry, yeah. So once we have the posterior distribution, our belief in the underlying rate of blue marbles, we can make a decision. And as we've seen, the decision can be modeled in many different ways, right? So one way is we can do a softmax. What is the softmax going to do is going to discretize, right? It's going to shrink a lot of the variance. And it's going to make the model more or less deterministically determined by the mean expected value. But that's not the only possibility, right? We could also say, actually, now we have a theta as a distribution. Let's just run a binomial on the full posterior distribution of the theta. Right? What does it mean? I have a slide, but I want you to have the concepts clear from the beginning. Let's say that you have average expected theta of 0.66. And my kids would want me to say 6.7. And this is going to be over a bunch of sampling from that 0.66. You're going to get this distribution of blue marbles. If instead we actually feed the full posterior distribution, given that there is all this extra variance, we're going to get something that is much more uncertain. Right? That's what we call the beta binomial distribution, which is combining the binomial with the beta that has determined the full distribution of the function. It's very elegant. We're going to use it. Whether that's how humans do it, who knows? They may be just doing the binomial. We could do it with model comparisons and see which of the solutions fits the data best. Yes.
So why is it, I mean, it might be very simple at the stone. I'm looking at the second line of the equation.
This one?
Yeah.
Yeah.
And I'm trying to understand why do we need the 1 on alpha and beta in the first place if we subtract them otherwise? Is it just to deal with the edge case that we have 0 observations?
But then if you have the -1, it's actually gonna go.
But if you ditch the -1 and the 1 altogether.
Oh, the prior?
Yeah.
Oh, no, we need the prior because we're Bayesians. We always have a prior.
Okay, but it could be it could be different than the prior.
Yeah.
We're just assuming here.
Yes.
It's not okay.
So in the course notes, you'll see that I present the Jeffrey priors, which some other people like Josh, which is 0.5, 0.5. And the course note explain why, but it doesn't need to be 1 and 1, right?
So why then subtract?
So here you would have like 0.5, and you still would have to have -1.
And the -1 because.
It's the formula of the beta distribution.
Okay.
It's probably a very deep question to which I don't have an answer. I don't work on like formulas of distributions. Yeah. I take them from Wikipedia. Yes. Good. So now we have all the tools we need to implement an agent that does rational, or I prefer to call it simple information integration. Right. We have the simple Bayesian agent, or SBA, which acts as a rational normative baseline. What do I mean by that? It acts as if the agent was following Bayes' theorem to the letter. This is how it would perform on whatever task we put it on. Since we know humans, you're now at your 4th year of cognitive science. Are humans rational and doing all the things you expect them to do? No, right? So this acts as a normative baseline. If we were following that, this is what we would do. And I like it exactly because it gives us a baseline. It treats all evidence at face value. There's a formula which is in, bad background. I haven't converted it, but it's what we've seen before. Alpha plus the number of cases, comma, beta plus the number of known cases. Right. Where alpha and beta are priors and k priors for us to be able to think of the model, and k is blue marbles, and n is the total marbles. So here I'm doing for seeing the red marbles is n minus 2. It's just convention on how you write these formulas. So every marble observed, no matter whether it's direct or social, counts exactly as 1 towards the belief. Right? Doesn't matter whether you sample it yourself or whether Christian has sampled it. Right? We just keep adding everything together. That's the rational choice. And I didn't mention that here it says alpha 0 plus the blue marbles in the first source plus the blue marbles in the second source. If you watch the video, you know that also we don't care how many sources there are, right? There could be 7. We're just adding all this evidence together. Everybody of you might be sampling from the same urn. We could add every one of you in the same form. We could look at the internet. We could have somebody telling us. We could sample. We could put all of these data together in the same format. However, right, when we talk about rational, it's kind of tricky to think of rationality in the abstract, right, and say there is always a best solution. For instance, if I asked my kids a few years ago, right, how many candies that you liked were in that urn, then the youngest one would have said, I don't know, I already ate them, right? Or 27. So should we trust all sources of evidence equally? Right? If you sample directly your marbles, and Nadia does it, but doesn't tell you what she sampled. She just says, I think it's 67% blue, right? You are going from a direct count of the marbles to a more indirect form of evidence. So you might downplay its confidence a bit. So, yes, there's a lot of literature on this. I'm going to skip because you know that we don't trust everybody in the same way. And that could actually be part of experiments. We can give differently reliable sources and see how people manage to evaluate them. But if we don't treat all the sources equally, we need to add a weight term. So where the posterior now is your original prior for blue marbles, plus the weight for the first source times the number of blue marbles from that source, plus the weight for the second source times the number of blue marbles for that source, right? And you could add, again, here there's no limit. It could be 7 sources, 1,002, right? It doesn't matter. And the beta is the same, but with the numbers of red marbles. And the weights note are the same because it doesn't matter whether Nadia is telling us red or blue, we trust her the same independently of the direction of the evidence. Right? If we have a weight of 0, right, we're just ignoring that source. If we give a weight of 0.5, we're saying that we're trusting it half. Like we're not taking it face value, we're downgrading it. And all the numbers between 0 and 1s are doing the same, different levels of underweighting. If we give it 1, we take the evidence at face value. If we do a weight above 1, we're overweighting the evidence. Right. Is this clear? Good. This kind of framework can be applied to a lot of different domains and tasks. For instance, the paper that was in the reading materials had a case in which you're sampling 8 marbles. These were red and green. And then there were 4 other people who were also sampling the same number of marbles. But then they were telling you whether they thought that the next marble was going to be green or red, and whether they were confident in that. Sure or not sure, right? So confident green, unsure green, unsure red, confident red. This is what we're going to talk through today and next lecture, the kind of task that we're going to sort of build up on, but only with another external source just for simplicity. The outcome follows a binomial distribution. You need to say whether it's green or red. When we model the evidence from my own sampling, how do we model it? It's not a trick question. It's an easy question. We need to tell it in my sampling how many observations of, let's say, red marbles there are. How do we model that? Yes.
Edit.
A number from 0 to 8. Yes, which can be added. Great. So that's easy. Let's say that we want to model this one. How do we model the evidence that we're getting from that woman? Remember, it's green sure, green unsure, red unsure, red sure. Yes?
So I can't really see the colors from here, but I guess we would say how many marbles she had and then wait.
But we cannot see it because we
No.
only get her decision.
We only get her decision.
Yes.
Estimate. The estimate.
Well, so she's betting on red,
Ah.
and she might be sure or not, or she might be betting on green, and she might be sure or not. That's all we see.
Okay.
That's where it's tricky.
Yes.
Yes,
We had 4 different responses, right?
yes.
So we have this is 1 to 4, and then they are either we have like 2 red options or 2 green options.
Yeah, so it could be from 0 to 3 if we want to keep the scale that goes from 0, right? We could say the other person decision corresponds to sampling 4 marbles, right? And we count if she is confident green is 0 red marbles. If she is unconfident green is 1 red marble. If she's unconfident red is 2, otherwise it's 3. This is very convenient. It's moving our evidence to the same scale in which we can make the model. What are the limitations? Or what is the assumption? Actually, it's not necessarily a limitation. What is the assumption of taking that person and putting it in a 0 to 3 scale? Yes.
Will they take 8 marbles per instance, and then we assume that they also have a sort of rational response to those marbles because we're not sure how each person has sort of a threshold for confidence, for instance,
Yeah.
in the next
one. Okay, so what we're doing is we are downweighting the evidence, which on the one hand might seem bad because they were sampling 8 marble just as us. On the other hand, might seem good because we only have that indirect evidence of what they sampled, and we don't know that woman, right? We might want to be careful or take the value of what she's saying, but sort of smooth the confidence a bit. If you think one step forward, when we'll do the weighted haze, then the weight might compensate. So it's not a big issue. Another way that we could do, which sent me a rabbit hole, is we could try to reconstruct the probability that she has picked 1, she had sample 1, she had sample 2, and get the full distribution, which again gets us in, we're modeling MCMC within MCMC, and that's messy. Right, we need to model a Bayesian sampling, Bayesian inference within the Bayesian inference, and it gets very messy. Yes.
I'm just wondering about, would you also need to model how the other agents update their belief across trials? What does that matter?
This is an excellent question. When we designed this study, we decided, fuck it, we don't want to do that. So let's be very explicit that the error is new every time.
Okay.
But we'll get, hopefully, I'm still working on the course notes on that, on a sequential Bayesian update. But yes, we could do that. But since, let's say that if we're modeling my belief at this stage, integrating my sampling and this woman, the next step, what I would do is I would probably need to keep track of my own evidence separately. So I'm just going to add the new social evidence. So not to get into these cumulative issues. For modeling purposes, we could do it, and it would be more complex and more prone to errors. I'm giving you the break in a second. Yes. Another case which I worked on is, the imitation inhibition paradigm. But basically is you are in front of a screen. When the number 1 pops up, you need to raise your index finger. When the number 3 pops up, you need to raise your middle finger. And completely irrelevant to the instruction, a hand appears on the screen together with the numbers. And that hand might raise the right finger or the wrong finger. Right? you're supposed to only look at the numbers. You shouldn't be influenced by the hand, but of course you are. So if they raise the wrong finger, your raising is slower. If they raise the right finger, your raising is faster and less prone to error. Does that make sense? You're integrating information. So there's a million different variants of that, but we have the outcome is in principle binomial, the index versus the middle finger. The predictors, right, are 0 if the middle finger is raised. 1 if, oh, sorry. There's two kind of predictors. Let's say now we're talking about the hand. It's a 0 if the middle finger is being raised by the hand, and 1 if the index finger is raised. And the other is the number. So if you had to raise the middle finger, it's a 0, and it's a 1 if you have to raise the index finger. And then you can just do the kind of update that we've been doing. If instead we want to take reaction time into account, we can actually, because in these studies, often we have that people make very few mistakes, but the impact on reaction time is quite visible. We can, for instance, invert the reaction time so that the slowest is close to 1, and then make it a positive number if it's an index choice, and a negative number if it's middle finger choice, right? Or we can constrain the variance of the Bernoulli using RT. But there's ways of using these extra information, right? So that we don't just have yes or no. And there's a formula there. And just the last point that I want to show before we take the break is that the task that you'll be working on in the assignment is a social conformity task where people have been asked to see 158, if I remember correctly, faces like this. And then they need for each of these faces to tell how trustworthy from 1 to 8 this person is. They get given a feedback. The other people in your class have actually rated this person. And there's a rating, which sometimes is the same as yours, sometimes it's lower, sometimes it's higher. Then these faces are shuffled, and you represented the 158 faces in a different order, and you need to give a second rate. And so your task will be to assess whether even in this shuffled condition, participants are still integrating the other peers' ratings and their own previous ratings in their second rate. Whether they're conforming to the general rating of trustworthiness of a person, blah, blah. In any case, let's take a 10 minutes break, and we'll get more into code and testing models after.
Jeg ved ikke, om jeg laver for
Okay, we'll start again. So we use a slightly simplified setup compared to the original experiment. We have a set of urns that change at every round with varying proportions of blue and red marbles. At each trial, the urn changes, so no learning is possible because we want to keep things simple. We'll see an example at the end of this module. At each trial, you sample n marbles, say 8, and that's source 1. And at each trial, another participant samples hidden to you and communicates their guess as to the next marble, including their confidence. And that's source 2. Source 1 and source 2 can be scaled to be on the same kind of scale, with source 1 going from 0 to 8 and source 2 going from 0 to 3. The experiment is built so that you get all combinations of source 1 and source 2, which is quite important if we want to identify how the model is going to work. We set up the experiment. Here is some code. It's pretty simple, but basically we're saying there's total 8 for the first source, total 3 for the second source. And then we want to use expand grid to develop all the possible scenarios. And red, of course, is derived deterministically from the number of blues because it's total not minus the number of blues. Then we have an agent that is using the beta binomial parameterization that we discussed to go through these trials and make their decision, right? So it takes the priors for alpha and beta. It takes the number of blue marbles, the total number of marbles in the first, the number of blue marbles, and the total number of marbles in the second source, and the weight for the 2 sources. We put as a default 1 and 1 because that's the simple Bayesian agent, right? Then we have that the alpha posterior is what we've seen before, the alpha prior plus the number of blue marbles in the 2 multiplied by the weight. The beta posterior is the same, but with red marbles. Just for visualization purposes, we calculate the average expected value. So the posterior estimate of number of blue marbles divided the posterior estimate of the total. We also look at the confidence intervals to do visualizations. And then we spit everything out. We also have the choice if the expected rate is major than 25, it's blue, otherwise it's red. Just putting the most direct conversion of the choice from mean expected belief to 0 or 1, blue or red. If we put the 2 weights equal 1, we have the simple Bayesian agent. If we put any other number, then suddenly we have the weighted rates. Here are just some examples of what happens when we run these models. We have that in gray is the prior, which is flat all over the place. On the x-axis, we have the proportion of blue marbles given the total. And on the y-axis, we have the oh yeah, so then we have that in the columns is in your own sampling of the marbles, how many there are, 1, 4, and 7, just to see some values. The rows are how many blues there are in the social source of evidence, 0, 1, 2, and 3. And then we can see in each panel, let's take the top one on the left, we have in red dashed the underlying, once you have 1 marble that is blue in the own sampling, this is the underlying rate given a D binomial, right? Distribution of rates. And in dashed blue, you have the underlying given the social source of information. And then the field distribution is the posterior. So we can see as the different sources of information vary, what happens in the posterior. And I inverted that. The blue was actually, sorry, the direct, and the red was the other person. Then we want, this is what I should have probably put it before because it's the point that I explained there. If we want to look at how the beta binomial actually works, this is the true underlying rate at point, I think it's 0.54, yes. And in red, we have the distribution of choices given a binomial, and in blue, we have distribution of choices given a beta binomial, right? Where we include the full, yes?
What does choice refer to here?
So you need to say, is the next marble gonna be red or blue? And then you repeat it over a certain number of times. I think it's 20 here, just to show you.
So about 20 trials.
Exactly.
Yeah, there's been a lot of times just blue.
Yeah. Because that allows me to sort of show the distribution.
Yeah.
So out of 20 trials with an average 0.54, right, the binomial is pretty much centered here and decays faster than the beta binomial. We can look at how the belief changes, the mean belief changes over time, given, not over time, but given how many blue marbles are in the direct sample. And with the colors, how many blue marbles there were in the social evidence. And what we can see is that the belief goes up linearly. And as we add evidence from the social source, it sort of linearly scales up. But the confidence is not linear. It's actually highest in the middle. So the uncertainty is highest in the middle. The confidence is highest at the boundaries. Because when you have 4 blue marbles out of 8, that's compatible with the most scenarios. Well, when you have 0 blue marbles out of 8, it's not compatible, for instance, with 100% blue marbles, right? So the distribution of probabilities is different. And if we run a bunch of simulations, in the middle, you see what we would expect the model to do, but the simulations are noisy, right? So we see that the true choices are a bit more noisy, depending on how many trials you put. And here is just another extra visualization where we represent the uncertainty, the size of the confidence interval, the credibility intervals, as we vary the number of blue marbles in the direct sample on the x-axis, and the number of blue marbles in the social evidence. Right? And as we see, right, it's really highest here in the middle. And yeah, that's about it. So the choice we made is not uncontroversial. So if we take the log odds trick that I had shown before, this is how the belief would change compared to how it changes in the beta binomial. What we have that instead of linear trends, you get these nonlinear curvy changes in belief. Anybody wants to guess why? Because when you move in log odd space, you're not moving in a linear space, right? So if you have that one source is giving you lots of blue marbles, and the other source is also going to give you lots of blue marbles, you're not moving as much in the belief space. Or you're moving a lot in the logout space, but it gets shrunk back when you go back to probability. So again, you can look a bit at your empirical data and see, are the assumptions of my model sort of following the one or the other? What's more likely to be happening? Okay, so this was just to sort of showcase the simple Bayes, but what if we vary the weights? We designed 3 scenarios. One in which the agent is self-focused. It puts a weight of 1.5 on self and 0.5 on the social evidence. The second is balanced just for comparison, is exactly the example we've seen so far, the simple Bayes, 1 and 1. And the third is the social influence. We put a 0.5 on self and a 2 on other. Yes.
And so right now we're just simulating these ways.
Yes.
We would want to estimate.
Yes.
Okay.
Once we understand the model.
Okay, because that's maybe what we're interested in.
Yeah, exactly. But before we understand the model, we shouldn't implement it. Right? And these kind of simulated data sets then can be used to test the models. So we want to see how these behave, right? And this is what we've seen before, right? The balanced one, the simple Bayes. If we have a self-focus, what happens is that the impact of the social evidence is squeezed, right? There is not as much distance between the 4 lines. And that the increase in belief is slightly steeper, right? Because we're overcounting the evidence from self. Does that make sense? And we're not taking it at face value, we're even overcounting it. For every 2 blue marbles that we see, given that the weight is 1.5, we act as if we had seen 3. If we look at the socially influenced, we see the opposite. Right? The increase in belief, given individual evidence, is not as steep, but the impact of the 4 levels of other confidence or other evidence is much bigger. Does that make sense? Yes.
You start this chapter also, but I confused every time I see, I don't really understand what the lines are and what the third lines are.
Okay, good. Yes. So let's focus on the full lines for a second, right? We're saying, given that there is these many blue marbles in my hand, as I said, 0, and that in the other person's decision, we see confident blue. How likely am I to pick blue as the next possible marble? Here it's about 0.2, but if we go to the socially influenced, it's about 0.5. Right? So even if I didn't see any, and even if the way we're coding for the evidence in the other is sort of down weighted just to start with, since I have a high weight, I'm actually much more likely to follow the other. And this is the 4 levels of the others. As we increase the number of blue marbles in my hand, how does that change? This is if we have, a model that's completely deterministic. But as we were talking about, we are actually sampling a theta value from this, and then running that theta value through the binomial. So the actual agents are going to behave much more erratically than the perfect determination. And so the dashed lines are some random runs of agents just to show how widespread they are. But they're confusing, you're right. Good. Then if we want to generalize and say, what if we continuously vary the weights in the agents and see how their decision vary? This is another way of representing that. So on the left panel, we see a case in which we have strong direct evidence, 7 out of 8 blue, and strong social conflicting evidence, 0 out of 3 blue. On the x-axis, we have the value of the weight on the direct evidence. On the y-axis, we have the weight on the social evidence. And the color is given by what the agent picks. And this is the ideal agent that doesn't shuffle around, but just takes. And so we can see that in this case, we have, so the black line is the, it's called the line of uncertainty, where it shifts from one choice to the other. And we can see that since, how was it? Well, the social has, in a sense, less evidence because of the way we code it. There is a much smaller area that's following the social evidence, right? Even if we give a lot of weight to social evidence. This is a way to understand the impact of our choices. Here, if we have a weak direct evidence, find 0.8, find 5 blue marbles out of 8 marbles, and a strong conflicting social evidence, 0 out of 3 blue, right? How does that change? And again, if we have a very weak direct, then which is as close to chance as it could be, just a bit on the blue side, then we get that it's getting more even between the two sides. But it takes a lot of weakening for the direct evidence before it actually evens out its impact. Good. So does these make sense as we're simulating forward, right? All these plots are just ways that I was devising to better explore how the models are behaving. Right? Now, what we can do is we can go and build the inferential model, right? Because what we want to do is to create a model that could be applied to empirical data and identify how much the participants are actually weighting the social and the direct evidence. Yes.
That makes me think of a question.
Yes.
So, given that the social information and the direct information is not on the same scale, if I was interested in saying something about if someone is more, if they are overweighting or underweighting social information, how would I account for whether the weight from the social information is just bringing that up to being the same level as direct information?
Yeah, you need to account for the fact that it's 8/3.
Okay.
Right.
So you can simply just multiply it.
Yeah. So what you could do is you could say, what if instead I rescale the 0 to 3?
Yeah.
So that it goes from 0 to 8. That would also be another possibility. So that would be an absolute. And since now we talked about number of blue and red marbles, but the alpha and beta can be continuous numbers, right? So it doesn't care if it's 5.6 compared to 5, right? So in that sense, if you wanted to do a direct comparison of the weights on the same scale, I would recommend rescaling the other. Yeah.
I have another one. What is the use case of this model? Like the consent to.
So there's, well, in those papers I was showing you, there was a larger project on the use of social information in schizophrenia. Because one of the theories in the field is that if you're getting less input from others, it's easier for your internal world to get sort of off track, because so much of our behavior and even perception is shaped by what we have around us. And what was, so I think what was coming out was that if you ask schizophrenic patients to use information from other people, they downweight information from other people more compared to non-schizophrenic patients or non-psychiatric controls. But if you don't give them explicit instructions about that, they overweight the social information more than the non-psychiatric patients do.
Yeah.
Which is interesting, but yeah. A lot of people have also used that in teaching contexts, right? So to understand whether your tendency to integrate information from the teacher, the instructor, is weighted more or less than your direct learning. It's been used to do models of what if I give you different advisors that have different levels of reliability. How are you weighting them? How good are you at sort of adjusting the right weight to them? Because that's also a very important skill. So there's some cases where these kind of direct versus social is being implemented. Yeah. In the conformity one, I think there was also a psychopharmacological study where they were interested in which kind of manipulations of neurotransmitters would affect the tendency of people to integrate information from others. I wouldn't, according to this, shouldn't say that, but I wouldn't trust those results too much because the doses were so high that a lot of the participants got sick. They really wanted to have an effect. Yes. Yeah. Okay. Did that answer? Yeah. So this is our simple Bayesian agent. The formulas are the one we've seen before, right? The alpha posterior is given by the alpha prior plus the evidence in the two sources, the beta posterior, blah, blah. And then the choice is given by a beta binomial, which is a shortcut for the theta is given by the beta of the alpha posterior plus the beta posterior. And then the choice is given by a binomial over the theta. We have the two parameters, the alpha posterior and the beta posterior, which are not real parameters because they're deterministically calculated from the prior and the likelihood. There is no free parameter to estimate. Those are the evidence that we see, and this is the choice, right? How do we code that? Well, the data as yes, let's see. So usually when that doesn't restart, right? What if I do off and then on again? Well, I can do it on the whiteboard because I don't want to start with that. Okay, but so if we have the data, right? What do we have in the data? We have the N, right? How many data points there are, how many trials. We have the choice, which is what is the agent picking? Which kind of variable is the choice? It's a binary, binary. It's an integer for Stan, which is a lower of 0 and a higher of upper of 1. And it's a vector because there's a choice for each trial. Then we have blue from the first source, total from the first source, blue from the second source, total from the second source, right? When we look at parameters, there's nothing. We don't have parameters we're estimating. And so the parameter part is completely empty. And then we have, maybe something is happening. The model. What is the model? Well, the model is our alpha cost. Oh, it's there. Yes. Right. You can see parameter is completely empty. Then we have the alpha post, which is determined exactly as we've seen before. Alpha 0 plus blue 1 plus blue 2. The beta post is beta 0 plus total 1 minus blue 1. So the number of red marbles plus total 2 minus blue 2. And the target is, so the likelihood function is a beta binomial likelihood function with a choice, one trial at a time, given alpha and post. Because otherwise it would have to be a beta Bernoulli. We don't want to write a 1, but I don't think it's implemented, or at least I couldn't find it. Now, we also have a transform data where I just use a different way of inserting the priors, the alpha 0 and the beta 0, just specifying them in transform data, but I could have put them in the data as variables that get fed from the data. Generated quantities, the log likelihood, the prior prediction, the posterior predictions. We do a loop throughout all the trials. We say that the alpha post is the same as here. That the beta post is the same as here. The log likelihood is the same as the likelihood function here. Right. This should be familiar by now. The posterior prediction are the beta binomial random number generator with the alpha post and the beta post. And the prior predictor are a beta binomial random generator with alpha 0 in the beta. Yes.
This might be a little bit of a tangent. It's about the Jeffreys priors. Is that the same as the JZS priors to Jeffreson?
So it's basically, so the idea is that the priors I like to use are the beta of 1, so alpha 1, beta 1, which in linear space are flat. And then Jeffrey complained that if we go to log space, they are actually pointy at 0, which is a 0.5, like they decrease at the side. And if you use a 0.5, it's much flatter. And so he thinks that on logout space, the logout space is more important because it's where things are estimated. I tend to think that the linear space is, or the probability space is more important because it's where we actually care. Yeah. But in the course notes, I compare models ran with both and show that the difference is very small. Yeah. Because I was also wondering, right? Does it actually make a difference? And it didn't too much. If we want to go to the weighted Bayesian, what we have is exactly the same as before, but we actually have two parameters that we want to estimate, the two weights. Which means that what we do now is we add the parameter in the parameter thingy. And we add those, the priors for those. And then, so I put a log normal, so we're sure that they don't go below 0 because we're making the assumption that people are not doing the opposite of what the evidence is doing, and that they have a long tail because they might overweight things a lot. But other choices are possible. And then everything else is really the same, right? We just add the weights wherever we have to bring in the evidence. So we fit them. We fit the simple model, and what we get is very fast, 200 milliseconds. Wording 4 out of 4 chains have a NANEBFMI. So when we try to calculate the energy of the sampler as it moves in the sampling space, we get another number. Right? That's usually a big no-no. What's going on? Now I was having fun doing slides. The suspense is killing me. Well, the model has no free parameters, right? So it's fully deterministic. That means that the Hamiltonian is not really running, which means we cannot calculate its energy. It's not a problem. Right? We can still calculate the log likelihood to see whether the prediction of the model, right, is supported by the data or not. It's deterministic, but we can still see how far it is from the real data, which we can use for model comparison, for instance. So we run the posterior predictions, and in the SBA, given that there is no learning, I'm not going to put two plots side by side because they're exactly equal. Right? And you can see in the balanced scenario, right, it's well in the middle, and it doesn't cover all the real data points. Oh, actually, I should explain what this is. Sorry. On the x-axis, as you use, is the number of blue marbles in the direct sampling. On the y-axis is the probability of choosing blue. And on the colors are the evidence provided by the social, the colored lines. And then and the vertical bars are the belief of the model. So there's 4 colors because for each level of direct evidence, we need to put 4 levels of beliefs of the model according to how much evidence there is in the social. But basically, what I wanted to show is that there's no change across the 3 scenarios because the simple Bayesian agent is not learning. It knows that it has to take things at face value, no matter what the data says. And so we can actually see that, for instance, a lot of the real data are completely out of the credibility intervals. Also here, but since a lot are here and up here, we don't see as clearly, but in this one. So this would already tell us that the model is failing, which makes sense because we're applying it to a situation for which it's not designed. The data has been generated by an agent that overweights social and underweights self. Then we look at the weighted Bayesian agent prior predictive effects. These are priors, right? So again, it doesn't learn anything in the 3 scenarios because it hasn't seen the data yet. But we can see already that it's much more uncertain because the weights could be all over the place. And that allows us, in principle, to cover all the data points. So it's already a nicer candidate even before feeding it to the data. Then we fit it, and we can see that the model is actually behaving very differently in its predictions. In particular, the socially influenced, you can see that the model is all over the place, but that's because the data are also all over the place. And we can see that the mean expected belief is actually much more widespread than in the balance sample and much less widespread in the self-focused sample, as it makes sense, right? So it's learning in the right direction. It's a messy plot. It's hard, like even if we're in a simple model, there's so much information that we need to represent. So we need to learn how to deal with complexity. Did you have a, no. So we then look at whether it can actually recover the parameter values in these 3 scenarios. we usually would run the systematic parameter recovery, the simulation-based calibration checks. But once we start working with complex models, it's nice to design simple scenario to test to see what's working and what's not before we go and let the computer run for 6 hours. Right? So we have only these 3 scenarios. We try to see whether the weight direct is reconstructed. We can see that the weight direct for the blue is centered on the true value, the vertical blue bar. For the green is centered on the green true value. For the red, it's hard to say, it's not really centered. It includes the vertical bar. But the uncertainty is pretty huge, right? So it's not doing a really nice job at recovering the weight direct. When we look at the weight on social evidence, things are actually even worse, right? The peak for the estimated weight direct in the balance scenario is very far away from the true value. And the uncertainty is even bigger than above, because the evidence in the social is smaller, right, for the way we coded it. So the model is not really recovering the parameters nicely, and we're seeing it even before doing the systematic parameter recovery. So what would you do at this stage? Well, actually, I'll just show you that this is not by, like, we were unlucky when we do the systematic parameter recovery. Well, here it's pretty flat. I do the thing brute force and I say, what if we had double the trials? It's still pretty flat. What if we have 4 times the trials? Gets better, driven by these extreme values, but it's not really where we want it. The uncertainty is still crossing all over the place. So what do you do when we get to these kind of scenarios where the model is not recovering the parameters? You have a raised hand?
Not quite.
Yeah. Yes?
I mean, this is more of like a specific to this case, but like you also said to me, don't we like structurally underestimate the weight of the social influence by having it on the scale that it is?
Good point. So we would go back and redo that. Then I promise you, we get something very similar. Yes.
I think maybe we could do without one of the weights.
Elaborate.
So now I'm just guessing that they're probably, I think this might be a problem with identifiability, I think it's called. That there are probably many combinations of weights that we get to save.
Yes.
So instead, maybe we could just look at a ratio of like how much are we weighting the social information compared to the direct evidence, and then we have less parameters to deal with. Good.
Okay, let me rephrase it. So there's one way of looking at that is saying, well, we have binary choices, right? Blue or red. And so if we have a weight of 1 for direct and a weight of 1 for social, we get a certain distribution of choices. If we have a weight of 2 and 2 for the sources, we get roughly the same distribution, just a bit narrower. That means that the model might have a hard time seeing that. If you're like me, it took me quite a long time to start developing these intuitions. So kudos that you can get it now. So how do we do and check? We plot the 2 parameters against each other. That's usually very telling. What do we see? Is we see a funnel. We see that there is a lot of variance here, and there is very little variance here, so that the model will have a hard time exploring it properly. What is these diagonal determined by? Well, we had, I think it was, this is the self-focus. So we have that the self is 1.5 and the the social is 0.5. So there's about a ratio of 3, and this is the slope that we get. If we were to look at the other, the socially influenced, we would get something that would look like this. So this is just another way of visualizing it closer by, where I visualize according to the prior, where it's nicely spread with some tails because it's a lot normal. But the posterior, the actual dots, is again showing the funnel. And okay, I don't have time to this. Go and look at this video when you feel very desperate about your modeling. It's a very cute cartoon about giving up on your scientific experiment. But then what we do is, and then using your friends to pick yourself up again. And then what we're gonna see next time is that we can reparameterize exactly to look at the ratio. One is to say there is only limited attention. Attention sums up to 1. And the two weights need to partition that attention. So the more attention you give to your samples, the less you give to the others. And so we have that the weight becomes P for own evidence and 1 minus P for the other person's evidence. So 0 is no attention, 0.5 is shared attention, 1 is exclusive attention. Or we can say that these two components are important. One is the ratio and the other is the total amount of attention. And so we separate the relative trust from the absolute weight in 2 parameters. We have rho, which is the relative weight, and kappa, which is the total evidence. And then what we'll do is implement these models and see whether we solve the problem. Again, it's another example of how to deal with failures of your models. Does that make sense? Good. So do you have questions? Yes?
So it's a question about the funnel thing.
Mm-hmm.
So it's the problem isn't that they're correlated as such. It's more the funnel in itself that's the problem. Or is it also the correlation?
In this case, it's also the correlation.
Yeah.
So another thing that we could have done is to say, given that the issue is the variance, and different regions of the space have very different variance, which is very hard to assess from binary choices, what if we instead ask people to indicate their confidence? So they have a slider that goes from totally blue to totally red, and they can move it around. Then we would have more information about the variance in their judgments. And that could allow us to know which of these regions is more likely. Are they varying a lot when there's this kind of scenario? Sometimes they go up, sometimes they go down. Then they're high weights. Are they varying little? Then it's the low weights. Does that make sense?
I think I was thinking more in general terms, like if the parameters are highly correlated, that's just intuitive, but that would be a problem for me, because then it would be easier or harder to
So the
model to disassociate them.
It's not just bad in itself that they're correlated. The bad thing is that it can really extend up there. So it's very underdetermined what the values are. If it were only this region, it wouldn't be as bad. So ideally, your model would have perfectly uncorrelated parameters. That would be the ideal situation, but we live in the real world. That's rarely going to happen. The sampler is able to deal with correlations. But in this case, the problem is not just the correlation, but the fact that it's sort of spread out all over. It's really hard to identify what's going on here, right? Because it really says all of these values are possible. Because if you increase one, you just need to increase the other and get exactly the same result. So you can get very far away in posterior space. And that's where the problem lies in this case. You had a question also?
I had a question, but maybe it can wait.
Okay, well, yeah, you should feel free to go, but I have a few more minutes if you want to ask it. Yeah.
I can see why we could solve this issue.
Mm-hmm.
It seems to me that a bit of functional, like splitting, is the right, like that just at least theoretically found, and then
yeah,
unless it's going to become very evident next time why we get to it, that it's computationally breaks down or something.
So the proportional or the yeah. So
What surprised me was that we didn't stop there.
Yeah.
Why did we need to propose an alternative? Because that's even.
Because okay, so my reason for putting that is pedagogical, because then we can see what happens when we have again these two parameters. But I can think scientifically there are theories about the inhibitory excitatory dynamics in schizophrenia, which have the impact of overcounting evidence. And so if you fix it at once, you're getting the ratio, but you're not getting whether they are overcounting the evidence. Yeah, right. You can only get whether they're giving more weight to this source or that source. So the idea would be that you could get much more confident. So you have one blue marble. Let's say 3 blue marbles out of 5, which should be quite broad. Still 10 about yeah. But what we observe in the schizophrenia patient is that it's like this. Right, so it's much more confident than it should be given the evidence. And you don't get that if you only do the proportions.
I can see why they're supposed to be. Can't really comprehend what that corresponds to that conceptually. Wait.
It's not, it doesn't correspond to, so it corresponds to very high weights.
Yeah.
Because you're so you're taking, so if your weight is, I don't know, 2, that's gonna say that it's really 6 out of 10. Which means that it's gonna be much more confident that the true underlying rate is 0.6.
Do we believe conceptually that you can think that way, like the mechanics of your mindset?
Yeah. So for instance, there's something called jumping to conclusion, which is a very well
So you kind of snap it into it.
Yeah. So you say, okay, there is a minimal evidence in that direction,
But if it's
I'm making a very confident
possible,
decision.
you have your.
Because there's very little evidence in my interpretation that it's red.
Yeah, because I think I'm just constrained by a preconception that, that like the whole nature of the word weighting is that like it's a dividing up of a space
Yeah,
that has a fixed size.
but no, actually you can overcount things. Yeah.
But then we also, so that we believe that the space is actually. Okay. I'll have to think about that.
Yeah. So imagine like you see a shadow and you think somebody's coming to kill you. That's taking a very slight view and making it into a very strong belief.
But then we would have to think, right, there is an upper bound to how much attention you can pay to anything. So we could,
But so there is an upper bound to the rate, but there is not an upper bound to how confident it could be.
right,
So in principle, these are the two infinite if you just concentrate there.
that's right.
When we
That makes
So that's where it makes sense. There's also something, so in the paper that I put in the reading,
What we have is like only
There's something called weights and loops. So if you take the sigma, there's really two components of the sigma. There's the slope,
Yeah.
and there's the still. Yeah. And so if you're, how is it? The weights are telling you something about how confident you can become. And the loops are telling you how easily you shift from the one to the other.
That makes a lot of
If
sense,
you're-
the spreading out of it.
Exactly. So if you're over counting, you're just jumping.
That's an intuitive explanation, because I can visualize the figure from the paper. Like,
Yeah.
that's a nice way of expressing that.
And in that case, they tried really hard to separate those two components, but actually maybe I should stop here, but I was running some